All right, just restarting OBS did the trick. So, where are we? We've found our first partial derivatives. We found our second partial derivatives. And what we found with those second partial derivatives is that at this point, 1272, we have a positive second partial derivative for both of them, which means it looks like it's maybe a minimum. For 0, 0, we've got one of them is a positive value. For the other one, it's a little bit trickier. For zxx, that value is 0 at that point. So I believe it's going to kind of look something like this, kind of a flat-bottomed parabola. But we'll ask Wolfram Alpha to do the hard work for us. Let's start by just asking, is this a local minimum? We need to check one more thing, and that one more thing is what is zxy. So let's take the derivative of this zx with respect to y. We're going to get minus 18, and let's just double check zyx. Take this derivative with respect to x, we also get minus 18. All right, so now what we need to do is we need to ask zxx times zyy, is that greater than zxy squared? Why does this work? I'm not 100% sure. I'm trusting the mathematicians. Intuitively, this is telling us, is there something weird going on, not just in north-south, but if we go up in any of these diagonals, does something funny happen? So zyx squared is a big number, 18, and 18 squared is 324, which I found earlier. Turns out 324 is a perfect square. And we're asking, is this less than zxx times zyy? Well, zyy we know is 3. And zxx is 18 times x. Well, what's 18 times 12? Well, it's something big. 18 times 12, right? So we're comparing 18 times 12 times 3 to 18 times 18, right? So if we divide both sides by 18, we're going to be asking, is 12 times 3 greater than 18? And 12 times 3, that's 36. That's twice as big as 18. Great, so this is a minimum, right? At least a local minimum. Nice, we have a candidate solution. We have this critical point, and we found out what's going on at that critical point. Now, the next question is, what about at 0, 0? Well, as long as we've got this math set up, let's take a quick look at what we would have. We would still have 3. We would still have 18 times x, but now this would be 0. So now we're going to have 0, and we're comparing that to some number. Well, 0 is definitely not bigger than this big positive number. So in that case, this isn't going to work. Let's leave a little frowny face to acknowledge 0, 0 is not going to be a local min or a local max. What exactly is going on there? Well, it's slightly funny, right? Since they are the same sign, zx and zyy, or I guess this is 0, this is 3, but we've got something that's kind of flat and something that's kind of opening up in the y direction. So it's kind of like a minimum, but it's not fully a minimum. So let's plug this over into Wolfram Alpha. Rather than watch me struggle even more with this math. So what are we plotting? We're going to say 3D plot z equals 3x squared. 3x squared, there we go, plus 1.5y squared minus 18xy plus 17. We want to think about what's going on at the origin. We know that it looks special, right? And hey, this kind of looks about right. And hey, there we go. So this is kind of, I don't know, for me, I would say this is just a diagonal saddle point, but we can also think of this as a sort of an inflection point. But what matters for us, right, what matters most is that it is not a local max or a local min. If you were coming from the northwest going down to the southeast, you would hit a maximum here. But if you were coming from the southwest and going northeast, you'd be hitting a minimum here, right? So it is very sadly, but this is what the function looks like. And let's go back to 1272. Let's try and maximize this. Is this a maximum? This is a minimum. I guess we could just say optimize this. No global minima found. I don't buy it. Oh, I made a mistake. We're going to have to look at that plot again. All right, this is good. So let's take another look at 0, 0. 0, 0 looks like it's happening about here. All right, that is much less sadly than what we had before. But 1272, is it a local minimum? It's kind of hard to tell from this, but they are telling us, Wolfram Alpha is verifying that we have this local minimum at 1272. It's not a global minimum. We can get a big small number by going off towards a big negative value of x and smaller values of y, but we are getting that local minimum. Let's go ahead and do 3D plot on this and see what it looks like at 0, 0. So 0, 0, can I restrict this to x? I wonder if this notation is going to work. Let's put x from -10 to 10. Oh, look at that. That worked. That was just a lucky guess. And let's say y is going to be in these curly braces from -10 to +10. Good. Hey, that worked nicely. So what have we got going on at 0, 0? Something funky, right? It's definitely weird. So in the north-south direction, it is flattening out, and in the east-west direction, it is flattening out. But it is also getting kind of twisted, right? So you can see in this case that you can move to a higher value by going northeast or southwest. The exact shape is kind of funny, but again, importantly, it is not a local max because you can go in this direction off in the diagonal and you can move to a higher value, right? So let's see what it looks like right around here. And am I thinking about this right? This kind of looks like it's increasing in this direction. It's a little hard to convert this. It would be nicer if I paid for the premium subscription and was able to do that. But in any case, what have we got? Let's go back to our notes. Our notes are a bit of a mess, but what we've got is, given this original function, we followed some basic procedure to find these first derivatives, and that was easy to do, right? What it means is maybe harder to wrap our head around, but mechanically, we're just moving some symbols around, and those rules for moving those symbols around are relatively straightforward. We move those symbols around, we set up to say, let's equal 0 for both of these, and let's solve for x and y. Now, it's easy to get lost in some algebra and take yourself down a blind alley and get the answer wrong, as I did and will continue to do in the future. In this case, we very fortunately had an answer, from the Sholmes guide, but even in your case, since our quizzes and everything else are open book, just throw it into Wolfram Alpha. Right? So you can always double check your answer. And in this case, when we double check it, this answer, we get that local minimum at 1272. 0, 0, we don't. Let's see why that's the case, and let's walk through our procedure again. So with zxx being this, zx equals this, zxx is the derivative of this with respect to x, treating y like a constant, which is just bring down the 2. 2 times 9 is 18, times x to the power of 2 minus 1 is 1, is 18x. Over here, derivative with respect to y, we get a 3. So we've got those derivatives. We find our cross-partial derivative, which was negative 18 for both of them. And when we check this third condition, that's when we really exclude this, right? But going through all this, right, using our first derivatives, we find our critical point, right? Just like we did with two-dimensional optimization. We find that critical point by setting that first derivative to 0. Here we're doing first partial set to 0, and we're finding a critical point that isn't in one dimension. Now our point is in 2 dimensions, right? Given that, then we check these second order conditions to see at this point where we flattened out, is it that we are moving to something smaller and we look like we're at a max, or are we moving to something bigger and it looks like we're coming from a minimum at this critical point? And then we check the cross partials to make sure nothing weird is happening in the corners. So in this case, when we check that over here, what we find is, doesn't matter the specific math, we find that zxx/zyy is bigger than zxy squared. We find that the effect of going east-west and north-south dominates anything going on in the corners, so we don't have to worry about it for this candidate solution. When we look at 0, 0, our other critical point, we didn't get that. This whole side turned to 0. This whole side was still 18 squared. So 18 squared is bigger, or negative 18 squared is bigger than 0 times a bunch of stuff. So in this case, the 0, 0 doesn't work, right? What exactly is it? We would call this an inflection point. It's not a saddle point in the way that we would have if, say, this was positive and this was negative, right? That situation where one is cupped up and one is cupped down. But it does kind of look something like that, just tilted at an angle. In any case, don't worry too much about what exactly is going on here. Just know that it's not a minimum, it's not a maximum. We don't really, in economics, do anything special with inflection points. Certainly not the math we're doing in this class. Saddle points, I think, are aesthetically neat, but they're not really a candidate solution. So just worry about identifying it as a max or a min, and that's good enough. All right, again, it bears repeating just to fit this into our brain. We've got a three-dimensional function. We find those first partial derivatives, set them equal to 0, and find critical points. Those are candidate local max and min points. Those are points where something interesting is happening because we're flattening out. If we're flattening out and we've got the correct configuration of second derivatives, then we can identify this as a max or a min, right? As long as this condition holds, nothing funny is going on in the corners that outweighs what's going on here, right? This is really what we're looking for. We're looking for maxes and mins. But if we've got something like this, well, we've identified an inflection point, or sometimes we'll identify a saddle point. What matters more is that it's not a min and it's not a max. So I really want to lay out the parallel here with the two-dimensional optimization. We look for where it flattens out, and then we ask, from where it's flattening out, is it getting smaller? Right? Is the slope going to something that's negative, so we must be at a maximum, or is it going to something positive, so we must be at a minimum? All right, now I hope that seeing this, again, this example worked through has been helpful. I hope it's also helpful to appreciate that We absolutely make mistakes. I've been doing this a million years and I'm still making mistakes. Don't sweat it. Don't take it personally. The key is to try to find out when you're making a mistake quickly and adjust. If I didn't look at the answer key and see this 12 and 72, I would have gone deep into this and I would have ended up with a bad candidate answer, but I would have just eventually found the mistake just later. And it would have been more costly to recover. But given that we have the appropriate approach, right, and we again catch mistakes because we still make those mistakes, the procedure involves a lot of this mechanical application of rules, but then just checking those conditions, following through that procedure helps us to narrow down what we're looking for and then identify where is it a minimum or a maximum. All right, as usual, feel free to ask your questions wherever.